Okay, so for investigation 4A, there are a series of terms that you're going to hear throughout this investigation, and one very important and somewhat confusing term that I want to talk about a little bit more in depth. So the terms that you're going to hear in this investigation are saturation. So think about a sponge. A sponge can only hold so much water before it becomes saturated. And then once it becomes saturated, if you add any more water to the sponge just leaks out that water. Well, the same is true with the atmosphere. The atmosphere can only hold a certain amount of water. And saturation is when it's at its max capacity. Now, that being said, what is max capacity? Well, believe it or not, these next two terms are going to kind of help with that. This first term is called vapor pressure. So if you don't remember this, air pressure is the pressure or the weight of the air above us, and the air contains all kinds of different molecules: nitrogen, oxygen, argon, neon, carbon dioxide, and so on. But it also contains water vapor, and that water vapor contributes to the overall pressure of the atmosphere, and we call that vapor pressure. This is just a fancy term for the content of water vapor in the atmosphere. So this is the water vapor content. Now, that being said, how much water vapor can the air hold? Well, that's actually what's called saturation vapor pressure. This is the pressure or weight of water vapor in a saturated atmosphere. This is the capacity. Now, that being said, the capacity changes with temperature. When air temperature is really high, that means that there's more evaporation. There's going to be a higher water vapor capacity. On the other hand, if the air outside is really cold, that means that we're going to have a low amount of evaporation and hence a smaller water vapor capacity. And there's actually a table that I'll show you in a few moments that will that you're going to be using in this investigation. And then finally, if you've ever opened up your phone before, or if you've ever looked at any kind of weather report and they say, the humidity outside is 78%. Well, what they're talking about is what's called relative humidity. This is a percentage of how saturated the atmosphere is. And as I just mentioned, it's given as a percentage. And the way that it works is to calculate this, you would take your water vapor content, that's your vapor pressure, and your water vapor capacity, that's your saturation vapor pressure, and you would divide vapor pressure by saturation vapor pressure, so you divide content by capacity, and then you're going to get some decimal number, like 0.6 or 0.7. You're going to take that number and multiply it by 100 to give you relative humidity. Now, you're going to do a few examples of this in this particular lab, but let's actually do one together real quick. So let's assume right now that the temperature outside is 76 degrees and we were able to measure a vapor pressure of 11.3 millibars. And there are ways to actually measure vapor pressure. You won't have to do that, I'm just going to give it to you. That being said, to calculate relative humidity, we would want to take our water vapor content, which is this right here, oops, and we're going to divide it by the capacity. Now, how do we determine the capacity? Well, we determine it by looking at the temperature. The temperature is 76 degrees, and what we then do is we take this temperature number and we look at a table that is actually going to be linked in the investigation, and I'll pull it up right now. And it's going to give us a saturation vapor pressure for that temperature. So let's do that real quick. Continue recording. I don't want to stop recording. So right here is a table that shows you different saturation vapor pressures for different temperatures. Now here's how this works. So there are three columns. The leftmost column is the temperature in Fahrenheit. Middle column is temperature in Celsius. Rightmost column is saturation vapor pressure. And we are looking for a temperature of 76, which would give us a saturation vapor pressure of 30.6 millibars. So let me just show you again. You would look at the temperature in Fahrenheit column and then go down that row until you reach the saturation vapor pressure. So 30.6 millibars. Now let's plug that into our number. Let's plug that into, so 30.6 is going to be right here. 30.6. And I'm pulling out my calculator right now. You are more than welcome to use your calculator when you do this. So 11.3 divided by 30.6 is 0.369 equals 0.369 and then 0.3693. I'm just going to round up to the nearest 4 digits. And even if you do nearest 2, that's totally fine. So then you're going to take this number, multiply it by 100, and that's going to give you 36.93%. If you were going to round just to make it a whole number, I would be totally fine with that. All that I ask is that you round up properly. So this would be 37%. And there you go. That's the relative humidity for this particular time. So you'll do this a few times in this investigation. And just to give you a quick rule of thumb, typically relative humidity is inversely related to air temperature. And this makes sense because air temperature is dependent, or saturation vapor pressure, this capacity, is dependent on air temperature. And the warmer the air temperature is, the bigger this capacity is. Which means that that denominator, the capacity, becomes bigger and bigger. That causes the overall fraction to become smaller and smaller. So in short, when temperature goes up, relative humidity goes down.